not hard, see you guys. And also, we're gonna start off with recognizing a few things that are going on right now. So the first thing is, hopefully you noticed that they gave us two different temperatures. They gave us 50 degrees Celsius and they gave us 25 degrees Celsius. It's key to recognize those things, even if you don't understand what the question is asking for firsthand. Recognize when they're giving you multiple things, because automatically that's going to give you one of these equations. And one of these equations are going to be used. Because when they're giving you two different things, especially if they're giving you a value of temperature, you automatically need to take Charles' law, and you automatically need to take V1 over T1 equals V2 over T2. Automatically, no questions asked. That's just the thing that you must think about. So for me, before I go into detail about that, let's go ahead and do some conversions. It's important for me at least, I think you should convert early so then you don't have to worry about it later. So remember we talked about how, liters, let's say this was in milliliters. So if it was in milliliters, it would have been, this would have been moved over 3 times, and it would have been 447.8 milliliters. If you wanted liters, you would have to divide by 1,000. But for degrees, we always, remember I told you that we always want our ideal gas to be in Kelvin. We have to have it in Kelvin. So with that being said, we have to convert Celsius to Kelvin. And that's easy. A simple formula to remember is just K equals value of degrees Celsius plus 273 Kelvin. Really easy to remember. You may not be able to see it, but it's literally this amount plus 273 Kelvin. It's not that hard to remember. And so with that being said, we do 50 plus 273. A lot of our little thinking caps here. And we get 323 Kelvin for this one right here. So we're going to put 323 Kelvin. And then right here we have 25. So we're going to do that one more time. We're going to do 273 plus 25.
And it's just
So we have 298 for 25. All right, cool beans, great. So we've converted our Celsius to Kelvin both ways. And we've also made sure that we have liters here. So let's read over the question again. Let's read over it one more time. It says that you notice on the Casimir is just like a replacement where the balloon goes. It's really simple. It's not hard. It's not really important. That's negligible. Of the unknown gas, which is what we want to know, that occupies a value of 0.447 liters at a temperature of, now that we have it in Kelvin, we're going to put it in Kelvin, 323 Kelvin, I'm sorry. You know the temperature of the room is 25 degrees Celsius. Identify the gas. So with that, since we have the liters, the value of the temperature as it is occupied on the capacitor, and we have the degrees as it's occupied on the capacitor, we can do V1 equals, remember when we talked about V1 equals T1 and all this other, we can use that formula now. That's cool, right? Yay, awesome. We can use the formula. So I'm going to put it down here.
what the what?
All right, so here it goes. We have our V1 over T1 over V2 over T2. It's like, why is she on the ground? She's trying to make sure you learn. All right, so you take your value, which is 0.4478 liters, divided by your temperature, which is 323 Kelvin. All right, and you set it equal to your V2. We're going to erase this stuff over here because it's going to get confusing, and I don't want you guys to get confused. I want you to learn something. V2 over, which we already have, are 298 Kelvin, right? So this is just simple math. If you remember anything about algebra, basic geometry, things of that nature, you don't. I know everybody remembers cross multiplication. Very simple. All you have to do, cross multiply and divide. Cross, divide, really easy. And so with that, you get value that is equal to X. Let me get my calculator. I'm a math whiz, but not that great. So you do 0, you do your liters times your Kelvin. And then you also divide by Kelvin. And you see with that, remember when we talked about we get rid of the things that we don't want. So we don't want Kelvin anymore. We don't want it. We're done with it. It's going to be whatever this value is that I give you, this is going to be liters per Kelvin. And with that, you can cross it out because it's one on the bottom, one on the top. I see it. All right, and our value comes to, let me get a different color so you guys can see it. Our V2 value, which is not our answer, we're looking for the ID, identifying the gas in the system. All right, so our value comes to 4.413 liters, okay? 0.413 liters, which is very important because we're going to use this, we're going to put it back into another equation that you will find very familiar. Yes, listen, this is time consuming. I know you're probably like, oh my gosh, why are we doing so much? Because it's, honestly, when you have extended problems like this, you're able to learn more about the different equations and how they apply to PV equals nRT. And then you're like, okay, you know, this is in advance, I'm ready for the test. You know, it's really easy. So, now that we have our value, let's make this big assumption. Let's make this huge assumption that we're doing standard pressure and temperature. Let's make this assumption. So with that being said, why don't we make this assumption that our pressure value is equal to 1 ATM? Because they ain't give it to us. We need it. So why not give it? Why not create it ourselves? Why not do that? All right. So we have a pressure value of 1 ATM, and we want to basically use this to solve for the number of moles in our system. So we're going to go back to the old handy dandy, you know it, we love it, PV equals nRT. Really basic, not hard to remember. Now I'm going to move over here and there's a lot going on the board, but I want you to get all of this so that you can see it all. Alright, so let's take the volume that we got here, boom, chop it up, we happy. Let's take that value and let's go ahead and plug it into the formula. Let's go ahead and do that. So we're going to take 100 ATM, which is negligible. It doesn't matter. It's just the value that we have. And we're going to set it. We're going to multiply against our configured value that we created, or we discovered, which is 0.413 liters, right? And we don't know what our N is. That's what we're trying to find. We're trying to find that, and we can't find it right now. So we have to just keep going. And remember I told you about this R constant? Well, here it is. Here's that constant with its own lettering. So it's 0.08206 liters times ATM over Kelvin times moles. Now this is so important. You know why? Because guess what? Boom, boom. All right, boom, boom. Look at that. Knocked it out. It's not there anymore. No, gone. Going with the next. All right, and then we're gonna multiply it by the value that they gave us, which is this one right here, the 298, because this is what we're looking for. We're looking for, you know, the temperature in the room is 25 degrees Celsius, and it's 298 Kelvin. So that's what we want. We want to figure out what that temperature is creating, that gas in that room. Identify the gas right there. So here we go. We're about to do it. All right, we cast out in Kelvin. Guess what we're left with? Moles. We're left with moles. Obviously, we did something right. We're doing it. We're doing it big. All right. So all we do is take this value here. Actually, we're gonna get this by itself. That's the big thing. We always don't want to create more work for ourselves, so we always want to put the value that we're looking for. We want to keep it by itself. So we want to take this and put it over here. So all you do is divide both sides by the amount that you get here. You cancel it out and you put it over here. Really easy, simple mathematics, but a lot of people forget it. I forget it sometimes. You know, it's basic. All right, so let's go ahead and get our values here. All right, so this came to 24.45, and then we're going to divide it by this. And I bet you're thinking, what? We're dividing a very, very big number by a very small number? But guess what? If you think about it, since our ATM is 1, what do you think? It's not going to be that large. Our moles can't be that large if our ATM is 1. Remember when we talked about how the relationship between volume and N? If our volume is this small, what do you think our moles are going to be? They got to be small too, right? So it can't be that big. For the number of moles in the system, I get N equals 0.16. Sorry, it's actually a very small number, 0.160. 0.0168. And we're going to just round that. I'm going to put that to 7. And that's going to be moles. Boom. Look at us doing big things. Look at us. All right. Now you remember at the beginning of the problem when they gave us these grams here? Remember that? You remember what they did that? All right, that's important. Now remember. Okay, you see where it says the balloon has a mass of this 0.5 grams, but it's completely deflated. Completely deflated. That's great. So that's basically saying that it starts at 0. So when it's completely deflated, this is how much it weighs. All right. When it is filled in unknown gas, unknown gas. Oh, we don't know it. Okay, fine. All right. The gas is increased to 1.7. So we want to know the difference. We want to know the change in that because that's the amount of mass that's in the is in the thing when it has that gas. When it has that unknown gas, we're trying to identify. So let's go ahead and do that. I'm gonna write it right here. There's a lot going on with my board. Alright, so 1.7 minus 0.5 gives you 1.2 grams. Oh, we just figured it out. I'm just kidding. Alright, so now that we have this, your molar mass is definitely gonna be like grams divided by moles, right? So we know that molar mass is grams divided by moles. So all you have to do is take this value here and divide it by that value, and it gives you, and you identify what the unknown gas is. Let's figure that out. It's great that we're getting this. Oh my goodness, we figured it out. I got a really large number. That's always good. Always good to get a really large. So our value came to, I'm going to put it over there. I'm going to put it over here. I want you guys to get it. So our molar mass, which is how we will be identifying the gas that was in the balloon, is equal to 70. 0.6 grams per mole, which is equal to, if you have a periodic table, you can use one, but this is actually equal to Cl2 because Cl is 35 and I'm a loss in my notes. Yep, Cl2. So we would then identify that our gas that is missing, we figured it out. So the Cl2 that was within the unknown balloon that we had to discover. So you see that it took like 5 different steps just to get one answer. Yes, that's with multiple problems that come from the PV equals nRT. Sometimes they're really basic and they just want you to find, they give you all of the variables and they want you to find one thing. But then sometimes you have to go ahead and use one of these to manipulate the equation so you get it. So you get the value that you're looking for. So with all that being said, thank you. Have a blessed one. I hope you enjoyed the video. Be great.